Imagine for a second that you're sailing this small boat through just a massive digitally rendered ocean storm.
Oh, yeah, just total chaos.
Right. Lightning is fracturing the sky. It's casting these really harsh dynamic shadows across the wooden deck of your boat.
Mm-hmm.
And you have these huge volumetric God rays piercing through this dense, swirling fog.
Yeah.
Plus, there's a flock of seagulls circling above you, and their flight paths are actually being calculated in real time while ocean spray is just whipping across the camera lens.
It's a lot.
It's a lot, yeah. You're entirely immersed in this chaotic, beautiful environment. But your computer is even breaking a sweat.
Right.
In fact, you're not even playing a massive 100-gigabyte game installation. You're running all of this seamlessly at a flawless 60 frames per second straight out of the standard web browser.
Which is, I mean, it sounds like science fiction if you look at where browser technology was just, a few years ago.
Yeah, guy.
The idea that a web page could serve as a high-performance cinematic stage, it was just unthinkable.
Completely unthinkable. But that impossible feat is exactly what we are looking at today in this deep dive.
Yes, it is.
And that brings us to the very special mission of today's show. We are speaking directly to a specific group of creators who are actually building this digital ocean right now.
The Bussin' Sigma Scholars of Edward Little High.
That's right. The Bussin' Sigma Scholars of Edward Little High.
We've been looking over the architecture of this digital playground that you all are currently constructing alongside Eric Eisenman.
And honestly, it's an incredible foundation.
It really is. We know the components you have in play here. You're building this interactive 3D ocean scene using Babylon.js 9.
Mm-hmm.
You have the drivable boat. You have a follow camera system. You have procedural terrain generation happening on the fly.
And those incredible flocks of Boyd's seagulls, which we'll get into.
Yes, we definitely will. Plus, you've got two incredibly distinct atmospheric modes, right? A bright day and a stormy day.
It is a phenomenal technical baseline. I mean, you have assembled all the heavy machinery required for a world-class simulation. But, having the machinery and making art are two very different things.
Oh, absolutely.
So that is the setup for today. We are going to guide you, the Sigma Scholars, on how to use the configuration files you've been given, the raw capabilities of Babylon 9, and the modern architecture of WebGPU.
Right, taking it from a really cool coding exercise and transforming it into a breathtaking masterpiece.
Exactly. We're shifting the focus from mere engineering into the realm of digital artistry.
It's about learning to paint with code, really.
Beautifully put. But there is a sacred constraint hanging over this entire project.
There always is.
Always. You have to achieve this visual wonder. You have to find that flawless balance of composition and sound and mechanics without ever dipping below the holy grail of 60 frames per second.
Yeah, and that 60 frames per second metric, it's not just a vanity number.
Right, it's not just for bragging rights.
No, not at all. In interactive 3D, we talk about this concept of glass-to-glass latency.
Glass-to-glass latency.
All
Okay,
right.
break that down.
So that is the total time it takes for a user to move their physical mouse, the computer to process that input, the graphics card to render the new frame, and then the monitor glass to actually display it.
Okay.
If you drop frames, that latency spikes. So the camera lags behind the user's hand, the boat sort of stutters on the waves.
It just feels awful.
It feels terrible. And the moment that happens, the illusion breaks. The user remembers they are just staring at a flat screen in their bedroom.
Okay, let's unpack this. Before we can start talking about adding beautiful storm clouds or perfect lighting, we need to understand the canvas you're working on.
Right. The foundation.
Yeah. We need to understand why your current procedural terrain and those thousands of Boyd seagulls are running smoothly in the first place.
Which means opening the hood and looking at the engine.
Exactly. We have to talk about this massive architectural shift from the old WebGL standard to the new WebGPU standard.
Yeah, the jump from WebGL to WebGPU is arguably the most significant paradigm shift in web graphics history.
Wow, really?
Oh, absolutely. I mean, WebGL has been the workhorse of 3D on the internet for over a decade, but its fundamental architecture reflects how graphics cards were designed back in, 2011.
Right.
WebGL is what we classify in computer science as a stateful API.
A stateful API.
Yeah.
Or a global state machine, right?
Yes.
Break down to what that actually means for a developer who's just trying to draw a scene.
Okay, so imagine you're trying to paint a house, but you have to dictate every single physical movement to the painter sequentially over a walkie-talkie.
Oh man, that sounds exhausting.
It is. In WebGL, there is this massive ledger of global state. You have to tell the GPU, bind this specific texture,
Okay.
then bind this geometry buffer, then turn on alpha blending, set the depth test to true.
Right, just one instruction at a time.
Exactly. And those states remain active globally until you explicitly send a new command to change them.
So the CPU, your computer's main processor, is the one constantly barking these orders over the walkie-talkie?
Yes. And it is highly single-threaded. So the CPU has to compile and submit all of these draw commands one by one.
I always picture WebGL like a single, incredibly stressed-out head chef in a massive restaurant kitchen.
That's a great analogy.
Like, the chef can only cook one dish at a time, shouting out orders for each ingredient sequentially.
Right.
And even if you have a massive state-of-the-art kitchen, which is your modern GPU, most of the stoves are sitting completely idle because that single chef on the CPU just can't shout orders fast enough to keep everyone busy.
That captures the bottleneck perfectly. The graphics card is literally starving for work.
Wow.
Is just sitting there waiting for the CPU to finish preparing the next instruction. But WebGPU changes that entire paradigm.
Because it abandons the global state machine entirely.
Yes, it is fundamentally stateless and asynchronous. Instead of shouting individual orders, WebGPU uses what are called immutable pipeline state objects, or PSOs.
Immutable pipeline state objects. That sounds pretty intense. What actually goes into a PSO?
Think of a PSO as basically a locked recipe box. It encapsulates all of the rendering states, your blending modes, your depth testing rules, your shader modules, all into one single package.
Oh, I see.
Yeah. And when you create this pipeline in WebGPU during the loading phase of your scene, the graphics driver validates all of those states up front.
Okay, so it checks its work before the game even starts.
Exactly. And once it's created, it cannot be modified. It is immutable.
Right.
If you decide you want to draw the ocean with a totally different blending mode, you don't change the state. You create an entirely new pipeline.
So how does that solve the stressed out chef problem?
Well, because the states are locked and validated ahead of time, WebGPU allows you to record these rendering commands across multiple CPU cores simultaneously.
Oh, wow.
Yeah, you are no longer waiting on one single thread to process the ledger.
So instead of one frantic head chef,
Yeah.
WebGPU is like having an entire team of sous chefs.
Precisely.
And they all have their locked recipe boxes in hand, and they are all chopping vegetables and plating dishes in perfect parallel harmony.
That parallel harmony is the defining characteristic of modern GPUs. And it leads us directly to the most powerful feature WebGPU introduces:
Which is?
compute shaders, which are written in WGSL, the WebGPU shading language.
Now, I know shaders usually deal with graphics, right? Like figuring out what color a pixel should be or where a triangle goes on the screen.
Right?
But compute shaders are different, though, aren't they?
Completely different. WebGL strictly restricted the GPU to graphics rendering. If you wanted to run a complex physics simulation or calculate weather patterns...
You had to do all that math on the CPU.
Exactly. You did the math on the CPU, and then you had to slowly send the results over to the GPU to be drawn.
Which goes back to the bottleneck.
Right. But compute shaders allow the GPU to perform general-purpose parallel computations.
And this is exactly how the Sigma scholars are getting thousands of seagulls to fly on screen without the browser crashing, right?
Exactly. The Boyd's algorithm calculating those flight paths, evaluating the separation, the alignment, the cohesion of thousands of birds simultaneously, that is pure mathematical computation.
Okay.
Your CPU might have, 8 or 16 cores, but a modern graphics card has thousands of smaller cores perfectly suited for parallel math.
Right. They excel at doing a lot of simple math all at once.
Exactly. By moving the Boyd's logic into a compute shader, the math happens directly on the GPU.
But if they are calculating all that math on the GPU, they still have to store that data somewhere, don't they? I remember dealing with WebGL limits a few years back, and memory was a constant nightmare.
Oh, yeah. Memory bandwidth was the other massive bottleneck in WebGL.
It was terrible.
When you wanted to pass a block of data, like the 3D positions of all your seagulls, you used uniform buffers, and those generally maxed out around 64 kilobytes.
64 kilobytes. That's practically nothing.
It's tiny. But in WebGPU, you have access to storage buffer bindings. These can handle 128 megabytes of data or more. It is a literal astronomical leap in how much raw information you can keep resident on the graphics card.
That is massive. But wait, if WebGPU uses a totally different language, WGSL, doesn't that mean developers have to translate all their old code?
Well,
Because I remember that being a massive pain for early adopters, having to import giant translation libraries that just bloated the download size of the web page.
You're right, that was a significant hurdle during the experimental phases of WebGPU, but the source material for the Scholars project notes that Babylon 8.0 and now Babylon 9.0, they handle this natively.
Oh, really?
Yeah, the engine natively compiles WGSL shaders. It completely removes the need for those massive transpilation libraries,
That's
which
so.
effectively shrinks the project download sizes by like 50%,
Yeah.
all while executing with absolute native performance.
Okay, I have to push back a little here, though.
Go for it.
If WebGPU is this incredibly powerful parallel processing monster, and the scholars have thousands of sous chefs at their disposal,
Hmm.
why do they even need to worry about that 60 FPS constraint? Like, if the CPU bottleneck is gone, can't they just throw infinite polygons, infinite storm clouds, and infinite seagulls at the browser? Why budget at all?
It's a very common trap. But removing the CPU bottleneck does not grant you infinite GPU power.
Right, there's still a physical limit somewhere.
Yes. You still have to pay the fundamental physical cost of transferring and synchronizing data across the computer's bus. But more importantly, you have to remember the platform you are targeting.
A web browser.
A web browser. You might be running this ocean scene on a thin laptop or an old tablet.
Right, this isn't a dedicated console sitting under a TV with a giant cooling fan.
Exactly. These devices are subject to strict thermal limits and background throttling by the operating system.
Okay, so what happens when it gets too hot?
If you push the GPU to calculate infinite polygons, the chip heats up. To prevent the physical hardware from literally melting or damaging the battery, the operating system forcibly throttles the power.
Yeah.
And the moment it throttles, your GPU clock speed drops and your pristine 60 FPS plummets to like 15 FPS. So the device will literally sabotage its own performance to save its life.
Yes, self-preservation.
So understanding that computational budget is absolutely critical. We have this massive power, but we have to wield it carefully.
Which introduces the artistic framework we really need to discuss today. Now that the Sigma scholars understand the realities of their budget, it's time to talk about how they should spend it to create a masterpiece.
We're moving from computer science to cinema. We need to talk about mise en scène.
Yes. Mise en scène is a foundational concept in traditional theater and filmmaking.
It's a French term, right?
It is. It literally translates to placing on stage. When film critics talk about mise en scène, they're referring to the totality of expressive content arranged within a frame.
Basically, everything placed in front of the camera lens.
Exactly.
The set design, the lighting, the shadows, the spatial proximity of the actors to one another. I think back to the French New Wave. You know, directors like François Truffaut or critics like André Bazin.
They use this exact concept to separate a mere technician from a true auteur. Like a technician just points a camera to record an event.
Right.
But an auteur manipulates every single element in the frame to evoke a specific psychological response from the audience.
And we are applying that exact same rigor to the digital realm here. The browser screen is a highly complex virtual stage.
And the Sigma scholars are the digital auteurs.
Yes. The way they utilize spatial blocking and composition in this ocean scene dictates the user's emotional state.
How does that apply to the two modes they're building, though, the bright day and the stormy day?
Well, space is a psychological tool. An empty, vast, clearly visible horizon implies safety and tranquility.
All right, you can see if danger is coming.
Exactly. That is the mise en scène you want for the bright day mode. But if you want to create tension for the stormy day, you clutter that space.
Okay.
You obscure the horizon with dense fog. You fill the foreground with swirling spray. You create chaotic, unpredictable lighting. You make the space feel claustrophobic, even though it's technically an open ocean.
But creating that vast space brings up a massive technical hurdle, doesn't it?
Oh, absolutely.
Because the ocean is supposed to feel endless. If a user gets in that drivable boat and they sail really, really far away from the starting point, the origin of the 3D world, the math starts to break down.
You are hitting on a classic limitation of 3D rendering. It's called floating point precision loss.
Right.
Computers represent decimal numbers using 32-bit floating point math. When you're close to the center of your 3D world, so coordinates 0, 0, 0.
It's origin.
The origin, right. The computer has an enormous amount of precision. It can calculate the position of a vertex down to a fraction of a millimeter.
Let's use an analogy for this. It's like measuring something with a ruler, right? When you're measuring a piece of paper on your desk, your ruler has these tiny, precise millimeter markings. You know exactly where everything is.
That's perfect. But as your boat sails miles and miles away from the origin point, the numbers get massive.
Yeah.
In 32-bit architecture, as the whole numbers get larger, The computer literally has fewer bits left over to calculate the decimals.
Wow.
To use your analogy, it's like walking 5 miles down the road and suddenly your ruler only has markings for feet and then eventually only yards. You lose the millimeter precision completely.
Oh, I've seen this in games. It's like the far lands in old Minecraft, right?
Yes, exactly.
Yes.
The math just gives up.
So what happens to the visuals in our ocean when the computer loses those millimeter markings?
Well, a vertex on the boat that is supposed to be moving smoothly suddenly can't find a precise coordinate.
Oh, no.
So it snaps to the nearest available grid point. The result is this violent, visible shaking and jittering of the geometry.
Which completely shatters the mise-en-scène. I
Yeah.
mean, if the boat is shaking because of bad math, the user's immersion is dead.
Immediately dead.
So how do the scholars fix it?
Babylon JS9 introduces a comprehensive large world rendering system, and it operates on a floating origin principle.
A floating origin,
Uh-huh.
okay.
Instead of moving the camera and the boat millions of units through the world space, the system conceptually locks the active camera at the origin, at 0, 0, 0.
Wait, if the camera's locked at 0, how do you sail forward?
You don't move the boat forward, you pull the entire ocean backward.
Oh, wow.
The system mathematically offsets the world around the camera. Because the camera and the immediate geometry surrounding it are always kept close to 0, the coordinates sent to the GPU remain incredibly small.
That is so clever.
So you keep your millimeter ruler no matter how far you sail, maintaining that pristine visual composition.
Here's where it gets really interesting, though. In a traditional film, the Truffaut movies we mentioned,
Yeah.
the director locks the camera down on a tripod. They physically force the audience to look at a specific, curated composition.
Right. You only see what they want you to see.
Exactly. But in this ocean project,
Right.
the user is driving the boat. They control the camera. They can look up at the seagulls. They can look down at the wooden deck, backward at the wake of the engine. How on earth do you maintain mise-en-scène when the audience is literally holding the camera?
That is the defining challenge of interactive spatial media. Because you cannot force the camera angle, you have to use a technique called signposting.
Signposting. So subtly manipulating the user into looking where you want them to look.
Exactly. You use environmental cues to pull the viewer's gaze. A distinct silhouette on the horizon can act as a signpost, but the absolute ultimate tool for signposting, the most powerful way to direct the human eye, is lighting.
Lighting.
Our brains are hardwired to track high-contrast pathways of light or movement in the shadows.
So lighting is our primary director's tool. Let's look at how the Sigma scholars can use advanced lighting to paint their two specific modes.
Okay.
Let's start with the peaceful side, the bright day mode. How do we make an empty sky visually compelling without eating up our 60 FPS budget?
Well, Babylon 9 introduces a feature called the Physically Based Atmosphere add-on.
Okay, what does that do?
In the past, creating a daytime sky just meant painting a blue gradient on a giant box surrounding the scene. A skybox.
Right, which looks super flat.
It was static and lifeless. But the physically based atmosphere actually simulates the volumetric scattering of light through a planetary atmosphere.
The sources mention Rayleigh and Mies scattering. We're getting into actual atmospheric physics here, aren't we?
We are. Rayleigh scattering is the scientific reason our sky is blue.
Okay.
When photons from the sun hit nitrogen and oxygen molecules in the atmosphere, the shorter blue wavelengths scatter across the sky.
Right.
Mies scattering, on the other hand, deals with larger particles like water droplets and dust. That creates the white glare on the sun.
So the engine is actively calculating how sunlight interacts with invisible molecules to color the sky dynamically.
Yes. It calculates multiple scattering events and even accounts for ozone absorption.
Wow.
If the scholars change the angle of the digital sun, the physics simulation automatically shifts the sky from a bright midday blue to a hyper-realistic deep red sunset.
That's incredible.
It happens natively in real time.
But a beautiful sky doesn't mean much if the boat feels like it's just pasted on top of the water.
Yeah.
It has to feel grounded in that light.
That is where dynamic IBL, or image-based lighting, shadows come into play.
How does that work?
Standard image-based lighting takes the colors of that atmospheric sky and wraps them around the 3D models to create realistic ambient reflections.
Right.
But traditionally, IBL couldn't cast shadows, it was just reflection. Babylon 9 allows the ambient environment light itself to cast accurate, soft, dynamic shadows onto the boat's deck.
So the ambient light of the blue sky is actually creating grounded shadows.
Yes.
That totally creates the tranquility of the bright day. But the stormy day requires a completely different emotional palette.
A total 180.
We talked about cluttering the space to create tension. How do we do that with light?
For a storm, you want to utilize volumetric lighting. This is the system that creates realistic light shafts, what we commonly call God rays.
Right, streaming through the dense storm clouds.
Exactly, or sea haze sweeping across the water. It gives the fog physical volume.
I know volumetrics are historically brutal on performance.
Yeah.
What is the engine actually doing to create those light shafts?
It uses a technique called ray marching. For every single pixel on the screen, the GPU fires a ray forward from the camera into the scene.
Okay.
As the ray travels, it takes tiny steps, it marches, and at every step, it calculates how much light is being scattered or absorbed by the fog at that specific point in 3D space.
That sounds incredibly computationally heavy. I mean, stepping through space for every pixel, every frame.
It is a heavy lift,
Yeah.
but Babylon 9 heavily leverages WebGPU compute shaders to run that ray marching logic in parallel.
Our sous chefs are back.
Exactly, making it exponentially faster than older methods.
Okay, but a storm also means lightning. And if you have lightning flashing all over the sky, illuminating all that fog, that means adding dozens of dynamic light sources turning on and off instantly.
Right.
I know traditional 3D rendering chokes and dares when you add too many lights.
That limitation comes from an older architecture called forward rendering. In a forward renderer, if you had 50 lightning bolts striking the ocean, every single pixel on your screen had to calculate its mathematical relationship to all 50 lights.
Even if the light was miles away.
Yes. The math just piled up and crashed the frame rate.
So how does Babylon 9 let the scholars put dozens of lightning strikes in their scene without dropping frames?
It introduces a system called clustered lighting. Clustered lighting divides the entire 3D camera view into a three-dimensional grid of individual tiles and depth slices.
Okay.
Think of it like a honeycomb stretching out from the lens.
Oh, I love this concept. It's like a hyper-localized mail delivery service.
Okay, I like where this is going.
Like in the old forward rendering days, every mail carrier had to walk to every single house in the entire country to see if they had a letter, right? It took forever.
Yes.
But clustered lighting divides the city into strict 3D zip codes.
That is a highly accurate way to visualize it. During the rendering process, a compute shader analyzes all the light sources, all your lightning bolts, and assigns them to their specific intersecting zip codes.
So the mail carrier, the GPU, only hands out light data to the specific pixels, the houses, that actually ordered it.
Precisely. Each pixel only calculates lighting from the 2 or 3 lights assigned to its exact 3D tile. It completely ignores the other 47 lightning bolts happening elsewhere.
That's brilliant.
The result is that a user can trigger the stormy day mode, lightning can fracture across the entire sky, and the browser maintains a flawless 60 FPS.
I have to ask a practical question, though.
Yeah,
The Sigma scholars have config files for all of this.
they do.
If I turn on ray-marched volumetric God rays and I have clustered lightning firing off,
Yeah.
even with compute shaders, aren't I begging for my laptop's thermal throttling to kick in?
It is entirely possible to overwhelm the system if you're careless. This is where the scholars must act as technical auteurs.
Right.
They have to open those configuration files Eric Eisenman provided and experiment. They need to tweak the extinction and phase parameters in the volumetric settings.
Rather than
Exactly. They have to find the sweet spot where they achieve the visual mood of the storm using the absolute minimum number of ray marching steps necessary. It is a delicate balancing act between beauty and performance.
Okay, so we've built this incredibly complex sky. We have God rays cutting through storm clouds. We have clustered lightning strikes localized to their specific zip codes on the screen.
It looks amazing.
But if we're building an ocean scene, all that sky is just sitting over a giant mirror.
Right.
If the water itself just looks like a flat piece of blue plastic, the whole illusion falls apart.
True.
The water has to react.
Which introduces the most notoriously difficult challenge in real-time graphics, transmissive media.
Oh boy.
We have to talk about refraction and caustics.
Explain caustics for the listeners. What are we actually looking at?
When light passes through a transparent, undulating surface like the rolling waves of an ocean, the light rays are bent according to Snell's law.
Right, physics.
Because the surface of the wave is curved, those bent light rays are focused and concentrated into intense, shimmering patterns of light that sweep across surfaces beneath the water.
Ah.
Those shifting webs of light are caustics.
Like the bright swirling nets of light you see dancing on the bottom of a swimming pool on a sunny day
Exactly.
or flashing against the wooden hull of our boat.
Yes. Now, if you wanted to render those caustics with physical perfection, you would use true ray tracing.
Okay.
The source material mentions a GitHub project called WebRay, built with Babylon.js and WebGPU. It demonstrates true path-traced caustics.
Wow.
It uses a bounding volume hierarchy, a BVH, to accelerate the ray traversal and temporal accumulation to blend multiple frames together to reduce the visual noise.
But wait, if I'm looking down through the surface of the water and I'm looking at the glass window on the side of the boat, the water is bending the light.
Yes.
But that glass window is also transparent, and it's reflecting the sky, which is reflecting off the water. Isn't that an endless loop of transparency?
It is.
Doesn't the computer get completely confused trying to sort out what is in front of what?
You have identified the exact problem the sources refer to as nested dielectrics, or what the French call mise en abîme.
A recursive, self-referential loop.
Exactly. Resolving these overlapping layers of transparent geometry requires a technique like dual depth peeling.
Okay, what is that?
It is a multi-pass process where the GPU has to render the scene multiple times, peeling away layer after layer of depth to figure out how the light bends through the water, then the glass, then the water again.
Multipass rendering, true ray tracing, temporal accumulation. All of that sounds incredibly expensive.
But you're far too slow for an interactive, sprawling web scene. If you turn on true ray-traced nested dielectrics, your ocean will look mathematically perfect, but it will render at 5 frames per second.
Ouch. So what does this all mean for the Sigma scholars? If true ray tracing is off the table because of their 60 FPS budget, how do they get those beautiful caustics on the water?
The solution for real-time engines is pragmatic. You fake it.
Fake it. Just abandon the physics.
You abandon the underlying physics, but you simulate the visual result. One highly efficient method is using what lighting designers call gobos.
Of gobo, like in theater lighting.
Exactly. A gobo is essentially a pre-rendered animated texture map that looks like a caustic pattern.
Okay.
You apply this black and white texture directly to a directional light source, and you simply project it down onto the boat and the water surface as if you were projecting a movie.
I'm sorry, I have to step in.
Go ahead.
Faking caustics with gobos. That sounds like a high school theater production using a spinning disco ball to simulate being underwater.
No.
If the scholars are trying to build an immersive masterpiece, doesn't faking it with a texture completely compromise the integrity of the scene?
I will counter that by returning to the core principle of mise en scène.
Okay, let's hear it.
The true art of technical direction is knowing exactly where to spend your computational budget. In real-time rendering, mathematical perfection is very often the enemy of immersion.
How so?
If you sacrifice your frame rate to calculate perfect Snell's law refractions, your glass-to-glass latency spikes.
Right.
The camera stutters. The illusion is instantly destroyed. Maintaining that flawless 60 FPS is vastly more important for psychological immersion than ensuring a light ray bends at the mathematically correct angle.
So the user won't notice that the caustic pattern is a projection, but they will absolutely notice if the mouse feels sluggish?
Correct. However, if the scholars want to push beyond basic gobos without melting their GPU, WebGPU offers a fascinating middle ground.
What's that?
They don't have to project a texture. They can calculate the waves dynamically using native screen space partial derivatives in the fragment shader.
Okay, you're going to have to translate screen space partial derivatives for me.
Yeah.
Let's break it down. In WebGPU, the fragment shaders, the tiny programs that determine the final color of every pixel, do not execute in isolation.
Okay.
They execute in tiny 2x2 grids called pixel quads. Because these 4 pixels run their code at the exact same time, the physical hardware can instantly compare one pixel's data to its neighbor.
So they can actually talk to each other.
Yes. In WGSL, there are specific mathematical functions called dpdx and dpd.
dpdx and dpd.
Right. These calculate the rate of change, the derivative, of any value across the x and y axes of the screen.
Give me an analogy for how that actually creates caustics, though.
Okay, imagine you and a friend are blindfolded standing next to each other on a rolling grassy hill.
Got it.
You want to figure out how steep the hill is without taking off your blindfold. So you simply reach out your hand and feel how high your friend's shoulder is compared to yours.
Ah, I see.
By comparing the difference in height over a tiny distance, you instantly know the slope of the ground beneath you.
That's brilliant. So the shader is doing that with pixels. It looks at its neighbor and says, how much did the height of this ocean wave change between your pixel and my pixel?
Precisely. By measuring that curve using those partial derivatives, the shader can approximate the curvature of the water surface.
Wow.
It uses that curve to concentrate or scatter the light on the screen in real time. It creates highly realistic, dynamically shifting caustic patterns based on the actual geometry of the waves.
But without the massive performance overhead of tracing a physical ray of light.
Yes, it is a highly optimized illusion.
A perfect illusion that keeps us at 60 FPS. Okay, so the sky is set, the water is shimmering beautifully using partial derivatives, but an empty ocean is dead.
It is.
The scene needs movement, it needs life. We have to talk about the environmental dynamics, the weather, the spray, and those birds.
We established that the scholars are using that advanced Boyd's algorithm running on compute shaders to handle the seagulls.
Right.
Boyd's is a classic artificial life program. It simulates emergent flocking behavior without animating individual birds.
Which saves a ton of time.
Yeah, it does. You just assign simple mathematical rules: separation so they don't crash into each other, alignment so they fly in the same direction, and cohesion so they stay as a group.
And because it's running on the GPU's parallel cores, 10,000 birds won't crash the browser.
Right.
But what about the stormy weather? The rain, the ocean mist splashing up against the hull of the drivable boat.
For the environmental weather, they should dive into Babylon 9's Node Particle Editor, or the NPE.
The NPE, okay.
It is a visual, non-destructive node graph. It allows technical artists to build incredibly complex particle systems without writing raw shader code.
Which is a huge relief.
It is. And specifically for a storm scene, they need to utilize particle flow maps and attractors.
Flow maps. I read about these in the provided notes. They are screen-aligned textures, but they don't store colors, do they?
Correct. In a normal image, the red, green, and blue channels tell the screen what color to display. A flow map encodes movement data into that image format. So the red channel might represent velocity along the x-axis, and the green channel represents velocity on the y-axis.
So it's like painting invisible wind tunnels across your screen.
Exactly.
If a pixel is pure red, the engine knows that any particle touching that pixel needs to be blown violently to the right.
Yep.
You can paint these textures to force the rain and the ocean spray to travel in perfectly choreographed, swirling vortexes around the boat. And what about attractors?
Attractors are invisible gravity points that you can place dynamically in the 3D scene.
Okay.
You can attach an attractor near the bow of the boat. As the boat crashes through the waves, the mist particles are mathematically drawn toward or repelled by that point, creating realistic splashes that react to the movement of the vessel.
Okay, I have to stop and do the math here. We have thousands of Boyd seagulls. We have thousands of rain particles following flow naps. We have mist reacting to attractors on a moving boat. Even if the GPU is calculating all this, isn't there a massive traffic jam transferring all those updated particle positions back to the screen to be drawn every single frame?
This is where we circle back to the fundamental brilliance of the WebGPU architecture we discussed in Section 1.
Oh, right.
If we were attempting this in the old WebGL standard, yes.
Yeah.
Calculating the physics on the GPU, reading it back to the CPU, and then sending it back to the GPU to be drawn would cause a catastrophic bottleneck.
The traffic jam would kill the frame rate.
Absolutely. But WebGPU handles memory differently.
Yes, the storage buffers.
In WebGPU, those compute shaders use storage buffers. When a developer allocates memory in Babylon using a specific flag, like Constant's texture creation flag storage, they are creating a massive sandbox of memory directly on the graphics card.
The 128 megabyte buffers we talked about.
Exactly. The GPU processes all the complex particle math, the flow maps, the Boyds, the attractors, and it writes the new 3D positions directly into that storage buffer.
Right.
Then, milliseconds later, the rendering pipeline reads directly from that exact same buffer to draw the particles on the screen. The data never has to travel back to the CPU over the system bus.
There is no traffic jam because the cars never actually get on the highway.
That's a great way to put it.
The data stays perfectly resident on the GPU the entire time.
The overhead is practically zero. It is an incredibly elegant closed loop of computation and rendering.
Wow.
And while we are discussing the environment, we cannot ignore the auditory mise-en-scène. The visual illusions must be anchored by sound.
The sources mentioned Babylon 9's audio engine updates, which align with modern web audio standards.
Yes. Sound is half the psychological experience of a storm.
Definitely.
Utilizing spatial audio engines means those Boyd seagulls don't just look like they're flying, they sound like they're physically circling the user's head in 3D space.
Oh, that's so cool.
When the boat turns, the sound of the engine shifts from the left speaker to the right. It deepens the immersion significantly.
All right, let's pull all this together. The scene has all its elements.
It does.
We have dynamic Rayleigh scattering in the sky. volumetric God rays, clustered lightning, caustic water effects, flow-mapped rain, and spatial audio seagulls.
Quite the production.
The final step for the Sigma scholars is stepping into the director's chair and balancing this entire massive production. And this brings us to what might be the most powerful organizational tool in Babylon 9,
The frame graph.
the frame graph. It sounds intense. What does it actually do behind the scenes?
The frame graph is arguably the most transformative architectural feature in the Babylon 9 engine. Technically speaking, it is a directed acyclic graph that gives the developer complete fine-grained control over the entire rendering pipeline.
Break that down for us. How is it controlling the pipeline?
Well, in traditional rendering, allocating memory for things like shadows, reflections, and post-processing effects is highly inefficient.
Okay.
You create a massive texture in memory to hold the shadow data, and that memory just sits there permanently, even when you aren't drawing shadow.
Oh, I see.
The frame graph changes this. You declare exactly what resources each specific rendering task needs for that specific frame.
Right.
The system then intelligently analyzes the graph and manages the allocation and reuse of textures on the fly.
So if WebGPU gave us 1,000 parallel sous chefs in the kitchen, the frame graph is the ruthlessly efficient stage manager of a Broadway play.
Yes, exactly.
The stage manager knows exactly which props and spotlights are needed for scene 1. The millisecond scene 1 is over, the stage manager snatches those props away, wipes them clean, and hands them to the actors for scene 2.
That is exactly what happens in the GPU memory. It ensures not a single megabyte of memory is left wasting away when it isn't explicitly serving the current frame.
That's amazing.
It results in massive memory savings, which is vital for browser-based experiences. Furthermore, it gives the scholars a centralized place to weigh the computational cost against the scenic contribution of every single effect.
Let's make this practical for the listeners. If I'm a Sigma scholar, I've got Eric Eisenman's config files open, I'm driving my boat through a stormy day, and my ocean scene is suddenly chugging at 30 FPS.
Okay.
The glass-to-glass latency is awful, the boat is stuttering. I look at my frame graph settings. What is the very first thing I should aggressively turn down or cut to get my frames back to 60?
The very first target in your frame graph should always be recursive transparency and complex refractions.
Right. The nested dielectrics.
Exactly. If your water is calculating light bouncing back and forth endlessly through multiple layers of mist and glass, cap the recursion depth. Tell the engine to stop calculating after one bounce.
Was the second target?
Volumetric shadow samples. Ray marching through fog is beautiful, but you do not need 50 ray marching steps per pixel to achieve a cinematic look.
Right.
Dial the step count down. If 10 samples give you 90% of the emotional mood of a storm, take the performance win.
Cut the fat.
Cut the fat. Remember the core rule of mise-en-scène applied to engineering. Every technical detail must serve a psychological purpose.
Absolutely.
If a visual element like mathematically perfect Snell's law refractions does not directly amplify the story or the emotional mood of the bright day or stormy day, it is just vanity.
Yeah.
Cut it. Your ultimate priority is the 60 FPS immersion.
That is fantastic advice. So to summarize the incredible journey the Sigma scholars of Edward Littlehigh are on right now, you start by understanding the raw, stateless, multi-threaded power of WebGPU and its compute shaders. You stop thinking like an engineer and step into the role of a digital auteur, painting your virtual stage with clustered lighting for massive storms and physically based atmospheres for tranquil days.
Exactly.
You make the hard, pragmatic choices for faking caustics with partial derivatives instead of true ray tracing to save your frame rate. And you manage the entire chaotic symphony using the ruthlessly efficient frame graph to achieve perfect digital mise-en-scène.
It is a...
You wave your hand, and a ripple mathematically propagates across the digital water. Or imagine an AI model that generates the volumetric storm clouds on the fly, matching the real-world weather currently happening outside your physical window.
That is wild to think about.
The web browser is no longer just a flat canvas for rendering code. It is rapidly becoming an immersive, AI-driven spatial computing medium. And developers like the Sigma scholars are the ones holding the spinning director's chair.